I guess it's nice to have span as an easy way to refer to all linear combinations of some set of vectors, but that doesn't really explain why it's important to be able to refer to all linear combinations of a collection of vectors. Why would you want to be able to refer to all possible linear combinations? Well, here's why. It turns out that if we have some set of vectors inside of a vector space, then the span of that set is a subspace of that vector space. And in fact, not only is it a subspace of the larger space V, it's actually the smallest subspace that contains the set we started with, S. So essentially, span is the operation that takes a set and gives us the smallest containing subspace. So, in linear algebra, what we're going to see is usually we want to work with vector spaces and subspaces. Well, if you have a set, it might not be a subspace. To turn it into a subspace, you just take its span. So let's see why this is the case. So the span is a set of vectors. We want to show that, first of all, that it is a subspace of V. Remember, to show that it's a subspace, we only have to show two things. We have to show that the span is closed under sums, vector sums, and scalar multiples. Okay, so first let's do vector sums, I guess. So closed under vector sums. Okay, so first we need to pick two vectors in the span of S. So let's take V and W in the span of S. Well, what does that mean? We want to show that the sum of them is in the span of S. Well, what does it mean to be in the span of S? That means V and W are both linear combinations of vectors in S. So let's write V as a linear combination of some vectors in S. So V is, let's say, A1V1 plus dot 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 down to, say, AKVK. And all the VI's are in S. Not in the span of S, but in S itself. And then also we can do the same thing for W. So say W is B1W1 plus dot 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 plus B. So we might not have the same number of V's as K's. So let's say BL, I guess, WL. And all of these W's are in S. Okay, so what is the sum of V and W? Well, that's V plus W is then all of these plus all of those. So A1V1 plus dot 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 down to AKVK plus B1W1 plus dot 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 plus BLWL. And all of the VI's and all of the WI's are all in S. So look, this displays V plus W as a linear combination of vectors from S. So V plus W is in S. And so we're done with this part. Now you might complain that, hey, isn't it possible that some of the V sub i's and W sub i's are actually the same? Wouldn't that cause a problem? Well, that doesn't cause a problem, and there are two reasons. The first reason it doesn't cause a problem is because in this definition of linear combination that we wrote down, this definition of linear combination, there is no requirement that the vectors that show up in this sum are different. So, it's possible to have repeated vectors and it still counts as a linear combination. The second reason that having a repeated vector wouldn't be a problem is, suppose there is a vector that's repeated. So suppose maybe, for example, that V1 is actually equal to W1. Well, if V1 and W1 were actually the same vector, we could just combine these two terms, right? So we could combine these two terms as A1 plus B1 times V1. And remember, V1 is the same thing as W1, we're sort of temporarily assuming. So if there are any repeated vectors, we could collapse the repeated vectors down to a single term, and so we'd still get a linear combination of these guys. All right, so one way or another, if we start with two vectors in the span of S, then the sum of those two vectors is also in, is also in the span of S. That's what I meant to write. So V plus W probably isn't in S, but it's in the span of S. All right, the second thing we need to show to know that the span of S is a subspace, we need to know that it's closed under scalar multiplication. This one's actually easier. So suppose we have V in the span of S. Then again, that means we can write V as a linear combination of vectors in S itself, like this. So A1, V1 time up through AK, VK. And again, all of these VI are in S. So then what if we multiply V by a scalar? Well, that's going to give us RA1V1, right? We can just distribute this scalar up to RAKVK. But I can sprinkle some parentheses in here like this. And this displays R times V as a linear combination of V1 through VK. So this is clearly in the span of S. And we're done. Right? We've shown that the span of S is closed under vector addition and under scalar multiplication, and so the span of S is a subspace. Right? No matter what set you started with, its span is always a subspace of your ambient space. All right. So it's nice that the span is a subspace, but really the reason that we care about it is that it's the smallest subspace that contains the set S that we started with. So why is that? So to show that the span is actually the smallest subspace in V that contains S, let's suppose, right, what does this really mean, the smallest subspace? Well, that means that if we have a subspace that contains S, it actually has to contain all of span of S. So what we want to show is if we have a subspace W in V and S is contained in W. So W is some subspace that contains all the vectors in the set S, then we want to show that actually all of the span of S is in W, right? So what this is saying that is if we have any subspace that contains S, it can't be any smaller than the span of S. That's another way of saying that the span of S is the smallest subspace that contains S. Okay. So let's suppose we have such a W. So suppose subspace W in V contains S. Then every let me say it this way. Then for every collection of vectors V1 through VK in S, the linear combination A1 V1 plus up through AK VK is contained in W, right? Why is this the case? Well, if all of these individual vectors are in S, S is contained in W, right? So every one of V1 through VK is in W. But W is a subspace. So W is closed under scalar multiplication. So if each of these v's is in W, then A1 times V1 is in W, all the way up to AK times VK, right? All of these terms, individual terms, are in W. But remember that W is a subspace, so it's closed under vector addition. So if these individual terms are in W, then the sum of these terms are also in W, right? So that means that this entire thing is in W. But look, this is a linear combination. This is a linear combination of vectors in S. So this linear combination, A1, V1, up through AK, VK, is in the span, also in the span of S, right? And in fact, every vector in the span of S is of this form, right? So what we've shown is that every vector in the span of S is also in W. I guess that's what I should have done to begin. Rather than taking these vectors, I should have taken this linear combination and then shown that it's in W. So, right, so this shows that span of S is contained in W. And that's what we wanted to show, right? Any subspace W that contains S also contains the entire span of S. And that means that the span of S really is the smallest subset, or subspace of V that contains the subset S. All right. To make use of the fact that span is a subspace, let's do this. Let's show that the solution set for any homogeneous system with n variables forms a subspace of Rn. So if we have a homogeneous system with n variables, then the solution set will be contained in Rn, right? Since we have n variables, a solution set will give values to every vector in the solution set will give values to each of the n variables, and that means each element in the solution set is a vector with n entries, and so that's why it's in Rn. But why does it form a subspace? Well, a while ago we proved that the solution set to any homogeneous system takes the form of A1 V1 plus ... plus AK VK for all choices of scalars here. So what we showed is that the solution set is equal to this for certain fixed vectors v1 through vn. Vk, sorry. There might not be n of them. All right, but now that we have the vocabulary of linear combinations and span, I hope you immediately recognize that this is just the span of v1 through vk. So this solution set is actually a span of v1 through vk, and so it is a subspace. We already know that every span is a subspace. Well, this is a span, so it's a subspace.